cats on the. Thank you. Okay, we're good to go.
Okay. First of all, thank you to the organizer for this very nice workshop, and thank you for the invitation to this panel. Today, I would like to discuss very briefly the structure of non-abelian gauge theories, specifically the case of gluons, the IR divergences, and the relation with the conformally subsector of celestial CFTs. This is a work in collaboration with Francisco Rojas, and previous work also have been made possible with because of Andrea Pum. Okay, so let me first start what happened to say what happens in the case of momentum bases. In general, gauge theories suffer from long distance singularities. So there are exchanges with states with very, very low energy. So at the loop level, this shows as divergences in the amplitudes. And you can find like a factorized version of these amplitudes where part of the amplitude contains the divergence, the divergent part, and there is another part, the hard piece, that controls the well-defined part of the process, let's say. So because of this factorization is made in an arbitrary scale, there are evolution equations that control this infrared divergent piece. So you have like a sort of an energy flow for these divergent terms. And here you define what is the so-called the anomalous dimension. Knowing the anomalous dimension allows you to find the divergent factor of these amplitudes.
I'm sorry, you're still showing the first slide, or you have gone to the next one?
I'm in the next one now. You cannot see it?
No, it's stuck on the first one, I think. Is that correct?
Okay. And now?
Yeah, okay, yeah. Now
maybe I will do it like that. Yeah, because I was sharing the whole screen. Okay,
sure, thank you.
So what I was saying is that, okay, so you have this factorized expression for the amplitudes, for the endpoint amplitudes, let's say gluon amplitudes, and you have a divergent factor that when you take lambda, the cutoff energy to 0, then becomes, of course, not well defined. But because there is this factorization happens when you separate the hard degrees of freedom from the soft degrees of freedom, and at an arbitrary scale, you have evolution equations for this factor that allows you to find exponential expression for it. Okay, so you can find them in terms of this quantity called the anomalous dimension. Okay, so here I will be mostly interested in the gluon case, and for that one uses the color space formalism constructed by Catani. Here in an n-gluon process, you have operators that are gluon charged in a sense because it satisfies conservation law, but also it's an operator that acts on vector space, on vector color space. Sorry. And very interestingly, in QCD, there is a very nice constraint, a very important constraint obtained by Gardi and Magnin and Becker and Neubert that allows you to restrict the soft part of the anomalous dimension in terms of a quantity rho here that it's invariant under scaling of the momentum of the particles. Okay, and well, this is the soft part of the anomalous dimension, and it happens to be equal to the cusp anomalous dimension. This cusp anomalous dimension is a number that you can obtain order by order in perturbation theory. Here, alpha S corresponds to the strong coupling. And the cusp anomalous dimension usually appears when you study renormalization properties of operators like Wilson loops in presence of this cusp, let's say. Okay, so this is a very nice equation because allows you to find this anomalous dimension in a more general way. I will not describe it. I will just go immediately to the celestial case, because what is important is that you can use that constraint to show that a similar factorization happens in the celestial bases, where now you have these factors C that is entirely defined on the celestial sphere. It's a color operator acting on this hard piece that is a vector in color space, and where now the conformal dimension has been shifted by a quantity that, as it happens in gravity and QED, it's divergent. So also very interestingly, this factor, this color operator, can be written as a correlation function of Wilson lines. And this is, like, here I quote the work by Gardy, Smiley, and White. Here, from this equation, you can see that these operators, these vertex operators or soft Wilson lines operators, have a conformal dimension that's without spin, and it's entirely defined in terms of this quantity K, that is the integral of the cusp anomalous dimension. So if you solve the RG flow for the coupling alpha, let's say in dimensional regularization, you can see that this integral will give you inverse powers of the regulator epsilon, let's say. So you can see immediately that this K is divergent. Okay, but still you can try to see if this vertex operator gives you a way to define a celestial CFT for this conformally soft sector. So these results, of course, are consistent with QED and gravity. And then here I am just citing all the relevant references. So let me show you some simple cases, and then I will discuss what happens in the more general case. So the simplest case in this construction, so if I would like to understand what is this celestial CFT that controls these degrees of freedom in the divergent piece, I can just consider first the planar n equals 4 super Young Mills, where the interactions, the soft interactions, only happens between the neighboring legs, external legs. So then you can define a vertex operator that will be given by the exponential of this term, where phi a corresponds to a color-free scalar. Of course, here you have infinite many colors, so then TAs are no longer operators, are just infinite vectors that satisfies the color conservation and only contains ones in the position I and I plus 1. And
now we have 2 more minutes, okay?
Okay, yeah. It's not very long. So also here, the BDS ansat allows you to find the hard piece, at least for the 4-point and the 5-point amplitude. And the Melling transform of this hard part exists because of the cusp anomalous dimension. Because of the positivity of the cusp anomalous dimension, sorry. So here I quote the word of Magnier that was very related to what I'm showing here. And you can also go, like, let's say, finite n, and using the dipolar approximation that has to do with describing the cusp anomalous dimension in terms of the quadratic Casimir only, and getting rid of the extra terms. And here again, you have a representation that is given in terms of free colored scalars. So beyond the Dipolar approximation, well, this is not very well known. What happens on the celestial case, because there are many complications, let's say the anomalous dimension start acquiring contributions. For instance, at 3 loops, you have functions that are SL2C invariant radius, but they have a very complicated structure. This was found by those people. And also at 4 loops in 2019 was found that there is another structure to the soft anomalous dimension that makes the conformally soft sector of this quantity a little bit less clear what it will be. So just to finish, one could ask, like, what happens if you consider Wessel-Minowitten theory as the theory controlling these degrees of freedom? So there is a very strong constraint that Wessel-Minowitten, the correlation functions of the Wessel-Minowitten theory satisfy this equation, the K-seat equation. And you can immediately see that at the level of the dipolar approximation already, there is an extra term on the right-hand side that does not allow you to fulfill this equation. So at the end of the day, set n is not compatible with Wessel-Minowitten model. One could wonder, like, is there any, let's say, deformation of Wessel-Minowitten model that makes the job here? Or let's say another type of nonlinear sigma model. Also, one could try to see if there are limits where this function, the set operator, simplifies. For instance, the high energy limit, the Rayleigh limit, and in this limit, one would like to see if there is some sort of a special theory controlling this specific case. This is it. Thank you.
Thank you, man. Okay, so next one is Suheng. We'll finish first with all our discussion leaders, and then we'll take questions. Okay.
Let me share my screen. All right. Can everyone see the screen? Okay. All right. Well, first of all, thank you for all the organizers for this very interesting conference. Today, I only have something almost trivial to comment on. It's probably too little for a full-fledged talk, but I think it might be appropriate for a short presentation at the panel. So let me begin. So during this workshop, we have seen a lot of exciting developments on celestial amplitudes and the related flat space holography. There are many general properties of the celestial amplitudes that were discovered and understood, such as those related to the soft theorems and many others. But however, as Andy and many others like to emphasize, there isn't a concrete top-down model for the celestial holography. It would be really desirable if we have something like in ADS CFT, we have the type 2 Shugura, which is due to the 4D super Yang-Mills. It would be great if we have such a top-down model where we, to some extent, understand a lot on both sides of the duality. And in this 10-minute presentation, I would like to discuss a little bit on arguably the simplest model for celestial holography, namely that for free field. For a free theory, we understand everything in the bulk. It might be a little bit too trivial to qualify as a top-down model that people are after, but it should be a good starting point. So let's consider free, massive, complex bulk scalar field phi in the d plus 2 dimensional Minkowski space. The Lagrangian is just the ordinary quadratic free field Lagrangian. The 4-point amplitudes of this massive theories is completely disconnected. There's no interaction. So we just have the 1, 2, 3, 2, 2, 4, and the 1, 2, 4, 2, 2, 3 disconnected amplitudes. Next, we apply the basis transformation to go from the momentum space to the conformal basis. Notice that I started with the massive scalar field so that there's a well-defined scattering process. And here I'm applying the massive conformal basis transformation. For the massless case, it's a little bit more subtle, but let me focus on the massive case. For simplicity, I will take the conformal dimensions for the 4 particles to be on the principal series, and with the imaginary part chosen to be this way. In this way, I can avoid certain contact terms, and I don't have a full understanding if I go away from this special choice. Then it's a one-line algebra to convert the disconnected amplitudes in momentum space to the conformal basis. The only non-trivial formula we need is the orthogonality condition for the bulk to a boundary propagator in hyperbolic space. At the end of the day, it gives rise to this formula. There's a prefactor that depends on the conformal dimension nu and nu prime. There's a standard prefactor for any conformal correlator. And then in the brackets, it's a very simple looking function of the cross ratio z and z bar. So let me just record the formula here again. Up to this prefactor here, the remaining piece is exactly the correlation function of a complex d-dimensional generalized free field with scaling dimension chosen to be d over 2 plus I nu. At least for this special choice of the conformal dimension, it is therefore tempting to say that a free scalar in the d plus 2 dimensional Minkowski space is dual to a continuum collections of the generalized free field on the celestial sphere. So what is a generalized free field? Let me give a lightning review on this conformal theory. It has featured prominently in a lot of the bootstrap discussion and also in ADS-CFT. The generalized free field theory is labeled by a scaling dimension delta phi. It is a conformal field. It's a conformal theory whose primary operator spectrum includes a single scalar field phi, the scaling dimension delta phi. So the 2-point function of phi and phi bar is given by W, the separation, to the 2 delta phi. There are other primary operators, but they can all be written as phi phi bar with derivative going in between. These are sometimes called the double trace operators, and they are related to the actual double trace operator in a full-fledged ADS-CFT correspondence. All the correlation functions in this generalized free field theories are given by the products of the 2-point functions. So for example, if we consider the 4-point function of phi, it's just given by the contraction between 1 and 3, 2 and 4, plus another one, 1 and 4, 2 and 3. And this is exactly the correlation function we saw by taking the disconnected amplitudes to the conformal basis. But let's put the celestial holography aside for the moment. The generalized free field theory has these simple correlation functions. And the correlation functions amid unitary conformal block decomposition and the intermediate operators that's being exchanged are precisely these double trace operators. The OPE coefficients are explicitly known and they can be written in terms of the gamma functions. Also, for this 4-point function, you can expand it on the conformal partial wave along the principal series. And the OPE coefficients for the conformal block decomposition, as well as the OPE functions for the conformal partial wave decompositions, have all been worked out explicitly in the literature. For example, you can see this paper from 2018. I'm not going to write it in this talk, but they are explicit function of the gamma functions. Generalized free field plays an important role in ADS-CFT. In the conventional ADS-CFT, the generalized free field is the boundary dual of a massive bulk scalar field in ADS with mass related to that parameter delta phi in the standard way. The generalized free field does not have a stress tensor for generic value of delta phi. So in some convention of the terminology, it might not qualify as a conformal field theory. Relatedly, there's no graviton in the bulk ADS. In ADS, we only have a free massive bulk scalar field. Still, this generalized free field is relevant for a lot of physical ADS-CFT correspondence. It can be thought of as the leading Largian limit of a scalar operator in a holographic CFT. The stress tensor only appears in the subleading order in the 1/n expansion in the scalar OPE. And in the ordinary ADS-CFT, the generalized free field is the leading order result in large N, and people have done a lot in going to higher order in 1/n by including various interactions. The generalized free field theory is called a free field theory because all the correlation functions are given by products of the 2-point function. It's called generalized because it's not literally the free field theory. In particular, it generally doesn't have a stress tensor. Only when you take this label delta phi to be the scaling dimension of a free scalar primary operator, it becomes the literal scalar field theory. So that's pretty much all I want to say. In the ordinary ADS-CFT, we know a free scalar in ADS is dual to a generalized free field scalar theory on the boundary. For the celestial holography, it's tempting to say that a free scalar in the bulk Minkowski space might be dual to generalized free scalars, with delta phi chosen to be on the principal series. But I put a question mark here because I don't think I fully understand this correspondence, except for the fact that that particular correlation function matches. What do we mean by a celestial free theory with delta phi chosen to be in this range? It's somewhat reminiscent of Liouville theory, but of course they're different in many aspects. And also it will be important to understand the contact terms that will appear for more general choice of the new I. But in any case, the disconnected amplitudes is the leading order amplitudes for many scattering amplitudes. And it's perhaps worthwhile to understand the celestial dual of this contribution. Okay, that's it. Thank you.
Thank you very much, Hank. Thank you. Tom, now, whenever you're ready. Okay.
Great. Okay, can you hear me, Gonzales?
Thank you, yes.
Okay, perfect. So we had already two excellent introduction to discussion. So I decided to go lighter and focus on this painting, which is appropriately called the School of Athens.
Yeah, that's right.
And, okay, we are supposed to be on Corfu, yes? Okay, so here you have Plato, we have Aristotle. Interestingly enough, at the center, you have a Diogenes, the cynic, okay, who's a famous, rather extravagant philosopher. This is actually a fresco, a painting, which you can see in Vatican Museum. It was painted by Raphael around, I think, 1510. And so you ask how it is related to what I'm going to say. Okay, this is the relation as follows. The question which sort of puzzles me, and I consider that I think really very important for formulating celestial conformal field theory, is whether to go Euclidean or Lorentzian. Okay, whether this two-dimensional CFT should be again, we should think about this as Euclidean theory or Lorentzian, or we should somehow go both ways. Like in 4 dimensions, we are Lorentzian, but we use Euclid. Well, at least I'm using, most of people are using Euclidean as a sort of auxiliary construct, okay, for analytic continuation and so on. But really in 2 dimension, Euclidean is very special, yes, because you have you may use, and that's what sort of became very clear in my yesterday talk, you can use the power of complex plane. And that allows really using standard techniques of Euclidean, of conformal field theory. Before I continue, let me go back to so the answer is clear, yes? For me. But what I want to do now is go back to here and focus on Euclid. There is something really very interesting about this painting. Okay, Euclid is surrounded by students, and just if you look at students, you think, well, Raphael painted made this painting in the 1510, okay? And so I find it really amazing. I mean, that this is actually the only character here who is really surrounded by students. Another thing which you can see here is that actually, if I can see right, Euclid is wearing a mask. Huh? Well, no, I think I told you it's a mural, but it is actually, I didn't make it up. Okay, it is there. Okay, it's really well. So he's surrounded by students who are, see, all of them are actually women, and he's wearing a mask. All of them running away from Diogenes, who's sitting here, and with okay, so who's sitting at the center? Okay, anyway, so going back to.
Before you leave that, Tom, who's the guy holding the celestial sphere there?
Oh, that's the celestial sphere. It's you know,
right above you.
It's the guy who's holding celestial sphere is Ptolemy. How you say it in English? Angelos, say it in Greek, okay?
It's Ptolemeos.
Ptolemeos. Okay.
Ptolemy.
Okay. So you have all characters here.
Characters from different era, but that's right.
Huh? Okay, so I'm going back to my remarks. Just have to move some stuff here on my screen. Okay. So now if you decide to go Euclidean for the purpose of this argument, okay, we may ask the question, where is the question which is actually asked very often if we give this talk, you know, in many places, yes. I mean, where is is this theory unitary? Okay, and I think what is most important, and that somehow we've agreed about it. I think everybody agrees that what is most important here is the 4-dimensional unitarity. Okay, that we are dealing actually with unitary theory. And so the question is how this 4-dimensional unitarity hiding in 2-dimensional CCFT, and whether this two-dimensional, whereas four-dimensional unitarity is any way related to two-dimensional unitarity, which you usually, for which you usually make a connection to Lorentzian two-dimensional theory. So you have to have a separate, still the central point, I think, is four-dimensional unitarity, okay? And so the question, how is it hiding? By the way, another reason for going Euclidean in two dimensions is that then we are using techniques which were developed over many years in CFT, and actually, after all, the goal of celestial photography is not just to describe the world as a hologram, and sort of appreciate it, but the goal is to understand four-dimensional physics better. So it is very important question to understand how these basic properties of four-dimensional theory are hiding or are implemented in two dimensions, yes? And we would like to get some new information about four dimension by using this two-dimensional approach. And that brings me actually to the next point, which right now we, I think, agree that we know more or less what are the two-dimensional conformal blocks. These blocks, for example, which are of the form integer plus I lambda. So one obvious question which you can ask, and I was sort of like trying to make this point yesterday, is what is the physical interpretation of the states? Whether you can learn something new about really Young-Mills theory. Yes? After all, the starting point is rather trivial so far for celestial amplitude. The celestial amplitudes that we are using to develop the CFT is a rather simple object. It's just all what we are doing here is playing with MH3 amplitude, yes? But whether understanding it from the point of view of two-dimensional conformality theory, we can learn something more about Young-Mills. And I wouldn't be really surprised if it happened. Same thing at my comment again about concerning my comment about actually when I was listening to Andy's talk, you have this beautiful structure of W infinity, which again is a two-dimensional CFT structure. Again, the question is whether this structure can be used to learn something new about the four-dimensional scattering amplitudes, for example, and to get some new information, understand, for example, soft theorems in more depth. Okay, so this is essentially all what I wanted to say, and thank you very much, and let's listen to discuss. Yeah.
Good. So, any I invite about the speakers or to the people that to the panelists. Any questions? Maybe from the talks earlier in the morning, or what was discussed today. Okay. So let me then ask, I think, Andy, which is related to what Tom asked. You found a W infinity algebra of some operators that I think they're related to subleading soft theorems. And there was a question as to whether they're universal. This universality has been always like, and already a comment was made by Atul, and I kind of agree that if you go to the MHV, you can write an infinite number of conserved currents. I'm talking about four-dimensional physics. But of course, when you consider general amplitudes, it seems that at least for, well, Young-Mills, the only universal is the leading, and then the subleading is not. But you found a new, let's say, set of of symmetries, but we can see them only in the two-dimensional CCFT. The question is, how would we see it in four-dimensional physics? Do you have any intuition about that?
Yeah, first of all, so let me just comment on the universality. So the leading soft graviton theorem was long ago in energy space, not the conformally soft graviton theorem, was long ago proven to be not to have any corrections. Now, so not to have any quantum corrections. Now, it's not completely clear that the universality of the energetic leading soft theorem implies the universality of the conformally soft theorem. And one of the issues there is that massive particles don't decouple in the same way. But it seems like it's probably true. And okay, so secondly, now let's go to the subleading soft graviton theorem. And somebody made a statement that the subleading soft graviton theorem gets a correction at one loop. Now, there's a paper by Byrne and Knoll and some other people in which they claim that. But what they do there is they put in an infrared, but what they say in that paper is correct, but I think it's been misinterpreted. What they do there is they put in an infrared cutoff. And then an infrared cutoff on internal loops, and they demand that the external state, so there's an order of limits there. There's a branch cut. Mm-hmm. And if you take the external particle to zero momentum before you take the loop momentum cutoff to zero, you don't get any one loop contribution. There's a branch cut. If you do it the other order, you do. Now, for what people have usually been doing over the years is at the end of the day, they want to compute exclusive amplitudes where they sum over everything with a cutoff. And from that point of view, the order that they took was correct, and that one loop correction is there and is needed to cancel something in the exclusive, in the inclusive cross section and so on. On the other hand, if you take the external particles to zero and keep the infrared cutoff on loops fixed, there is no one loop correction. And this was proven in a paper by, it's sort of obvious, they agree with it, but it was proven and written out in a paper by Cacciazzo and a student whose name I'm not remembering. So in everything that's been done in this conference and all discussions of the subject, we always are scattering Mellon primaries, which means that we've integrated their momenta all the way down to zero. And then if we want to compute loop corrections, we may need to put a cutoff on those loop corrections. So we will be, in our context, the Cacciazzo analysis is the relevant one, and there are then no corrections to the subleading soft theorem. And indeed, at the end, another story, we should be using, clouds of soft photons incoming or outgoing to cancel the infrared divergences, and then we never need an infrared cutoff at all in the first place. And indeed, the Byrne identity was 0 equals 0 because infrared divergences set those things to 0. Now, okay, so that's the situation with the subleading soft theorem. But now the leading symmetry and the subleading symmetry, the leading and the subleading symmetry, you can't commute them and get all the rest of them. So the sub-subleading symmetry is really important. And the sub-subleading symmetry is, now it's known that there's some ineffective field theory, and there are a number of papers on this, particularly nice one by Elvang, in which they show that there's some finite list of higher dimension operators that can correct this. However, as far as I understand, if you look at what that means, those corrections come in when you have an OPE of a positive and a negative felicity thing. So I think the sense is, and I've even seen this, I think I've seen this claimed in some papers, that this W algebra is a subset of the symmetries that act on hard amplitudes. And there was a paper by Mina and Monica and by Hongleong Jiang showing that, explaining that how these W generators act on the hard particles. So I would say that these W probably this has to somehow, probably this survives loop correction, so maybe gets deformed, and probably certainly in the classical limit, it should act on all the tree amplitudes, all physical tree scattering amplitudes. So I mean, what could be a more direct statement about the real world? I mean, it's some statement about symmetries that act on scattering amplitudes.
Considering loops, I thought that the sub-subleading graviton theorem does not have a universal form. I mean, it doesn't have the form of just, well, if I remember correctly, or at least beyond that level. I remember an analysis by Byrne that once you were going the small energy expansion beyond the sub-subleading order, you didn't have a universal form of writing down a soft theorem for that. It was dependent on the form was not fixed. It's not, doesn't have the form that you have in your paper with Kachazo with the angular momentum.
That's why I said at tree level.
Yeah.
At loop level, the sub-subleading, so we want it to be deformed. We'd like it to be deformed to this capital W. And the hope would be that that this deformation turns little w into capital W. I mean, that would be like all wonderful things happening at once. Maybe the story is much more complicated.
Okay. Let's see. Okay. Yeah.
I mean, the bad thing that could happen is it could be somehow explicitly broken.
Right.
Well, I mean, even that, there would still be information in it. When you have, you know, classical symmetries that are explicitly broken by quantum effects, you still get some relations, but they'd be under much, I think they would probably be under less control.
Mm-hmm. Tom, you want to ask something? I think you're muted. You need to unmute. I press on the button.
Okay, it's hard to, I couldn't find myself on, because I have a full screen, okay, I couldn't find myself among the participants. Okay, so it's related to the universal, again, related to the universality issue, okay. It's a my very primitive way of thinking is as follows. If I have subleading theorems, carry actual information about energy dependence, yes, of the amplitude and momentum space. So if I knew everything about those, if I had all sub-leading and sub-sub-leading theorems, if I were able to understand them, then I could use this conformal soft theorems to reproduce the amplitude. Yes, so somehow the full amplitude, full energy dependence of a scattering amplitude, Young-Mills or a gravitation amplitude, could be determined by the by your coefficients of W algebra.
I don't think so, because well, we already know. I mean, for sure, these things are there at tree level, and they're there at tree level with, you know, gravity coupled to arbitrary matter representations and arbitrary massive fields and whatever. So, I mean, if you have a theory, two things. If you have a theory with an infinite number of symmetries, it doesn't necessarily make the theory integrable or determine all the amplitudes. Obviously, we can take two decoupled theories, one with an infinite number of theories, and add some other messy theory, which it doesn't touch. So, and then, you know, so infinitely many symmetries does not imply integrability. And the second thing to say is that in gravity, once you have the the leading, the subleading, and the sub-subleading generate by commutators all the symmetries. So you're not getting any new constraints on the scattering amplitudes. If you show that the scattering amplitudes are consistent with those first three in gravity and the first two in gauge theory, then you're done. It has to satisfy the whole tower. But I agree. I mean, when this business started, it seemed crazy that you could, you know, even in ordinary conformal field theory, they seem so highly over-constrained. It seemed very hard to imagine that you could add on that. I mean, just adding translational symmetry seemed like too much. But, you know, we have constructions of these things.
Constraints.
I have a comment or maybe a question to the first talk at this panel. So in ordinary WZW model, the KZ equation arises because the null states have to decouple. In the celestial sphere, I'm still rather confused by the norm. And maybe, is there a rule that the null states should decouple? And maybe it's because the null states are still there, and therefore the correlation function you find, or the amplitudes you find, don't necessarily obey the KZ equation.
Okay, so I don't really know about like the null state in the IR case. But we just tried, like, because it's a correlation function based on a SUN symmetry, and
yes,
and it's a two-dimensional, it should be a two-dimensional CFT. So we try by checking if this correlator satisfy that equation, and like, yeah, because that would be the naive guess, let's say. But
right,
it ended up not working.
But the fact that it doesn't satisfy, I guess, exactly implies that the null states are actually still there. It's a non-trivial operator that has non-trivial correlation function with other.
You're right.
States.
You're right. Yeah. But
you say it still satisfies some differential equation, just not exactly.
Well, there is a left-hand side. Yeah, it also, sorry, a right-hand side. You have something, but you also find an expression that it's a power series, let's say, because it's an exponential ansatz. So then you get like a series of terms. You don't get only one, you get many. Yeah, yeah.
Is it that
And
the content of KZ equation essentially that the energy momentum tensor of Shugabara form? Yes, that's the.
Yeah.
If I understand it correctly.
That's right, and
Yeah.
that's equivalent to say that at that level,
Yeah.
maybe level 2, there's a null state.
Yeah, but in celestial CFT, we at the end we know that there is more to an energy momentum tensor than Shugabara form, so you don't expect it to satisfy.
Right.
So can you, oh, sorry. Francisco, yeah, go on, please.
Thank you, Angelos. I just wanted to ask Shuheng, do you think that in some limit, for example, it seems like in the Reggie limit when the conformal cross ratio, at least for the 4-point function, when that in the limit when that goes to infinity, it seems that in powers of 1 over the cross ratio at leading order, the Nishini's homological equation appears. Apparently, I mean, we're still working on these things. Do you think that in that limit, maybe this null states decouple? Could that be
which null states? The null states of the WZ of the Kac-Moody, or which null state? Sorry.
Or maybe I misunderstood, but if I understood correctly, you said that the fact that this subfactor does not satisfy the KZ equation,
right,
was somehow of a signature that these null states are still present.
Yes.
Is that true?
Yeah, I think, yeah, that's how the KZ equation was derived for ordinary WZW model.
Yeah,
yes.
Okay, yeah, yes, okay. So since this KZ equation seems to appear in the Reggie limit, does that make sense in the sense that maybe in the Reggie limit, this null states somehow disappear or decouple? I don't know.
Maybe, I don't know. I mean, I didn't really study that correlation function. Like maybe Hernan can say more. I just heard the talk and I don't know any details of that correlation function.
That's right, okay, thanks.
Yeah.
So, okay. So Andy wants to ask something. Yeah, go on, please.
Shuheng, if you had done the same calculation for free gluons, would you have had the same kind of states that Tom had of conformal blocks that were in the biadjoint of?
So first of all, yes. So there is a vector version of the generalized free field that certainly exists. Now the question is, what are the primaries in the generalized free vector field theory? Now let me think. I think there will be such operator because they are the. Well, let me think. No, but I think I will only have the double trace operator. So the scaling dimension would will be d over 2 plus I nu and possibly d plus I nu. These are all the primary operators. Oh wait, hold on, maybe I'm wrong. No, but they are, sorry, but then you can decorate with the angular momentum. You
had intermediate states that you
were
associated with operators like phi,
Right. So yeah, you are right. So those can potentially, so the dimensions for those guys will be an integer plus I nu.
So this phenomena that Tom was mentioning about needing to discuss states that are in the biadjoint,
right,
appears in this,
right,
already appears in this at the level of free.
Yes, I would say so. Yeah, so you can take the free field correlation function and just this sum of the two disconnected pieces. And you can expand it on conformal blocks, right? This is a math questions, and people have done it. And indeed, all the intermediate primary operators, their scaling dimensions are always an integer plus I knew. So yeah, that's a good point. So indeed, what Tom and collaborators observe already appear for a free field.
Right, and there's no way on Earth you're going to associate those with states of a single.
Right, I mean, they're double trace operators. They're like bound state.
Yeah.
So I guess one thing is that, so in ordinary amplitudes, at least in 3 or higher space-time dimensions, there's an invariant way to separate the disconnected piece versus the connected piece, right? They have different supports on the whole phase space. One of them is a product of delta function, the other is only a single delta function. One can ask, is there a similar separation for the, well, once we go to the conformal basis? I haven't thought about it very carefully, but I suspect the delta functions in nu in the conformal dimension might be different for the two. And what Tom was doing was for the connected piece. So yeah, anyway, I don't know, but there may or may not be an invariant distinction or separation between the disconnected and connected pieces.
I'm sorry, Soo-Hyang, you said something that if you have the disconnected piece, or maybe Andy said it, you can get the conformal blocks. Maybe I missed that or I misunderstood. What? How would you do that? Because
maybe I can just share screen.
Yeah, sure.
So you can start with this. Oh, actually, what I wrote here is for a real generalized free field as opposed to a complex.
Oh, that was my
generalized. So it has an additional term because now you have 3 different contractions. And the conformal block decomposition of this function has been worked out in the literature, and it takes this form. And you can see that the intermediate operators, their scaling dimensions take this form. So it's 2 times the external operators, delta phi, plus an integer. Yeah. And all these coefficients are known explicitly. Let's see here.
And you say this corresponds to double trace operators, is that correct? But,
yes, yes. So all these operators, they are of the form phi, they're quadratic in phi, and they have several derivatives acting on them, and therefore it increases the scaling dimension by this much.
I think this is generic Granite CFT. You will have your power expansion in X. You will have these blocks with only in minimal models. Then actually, miracle happens because the descendants end. Yes, I mean you have null states. But
yeah, here
you will have all spectrum of all conformal blocks. Yes,
that's right. That's right.
In the Yang-Mills conformal block expansion, do you get like one conformal block for each Kac-Moody descendant? So are these bi-adjoint and higher adjoint objects just Kac-Moody descendants somehow? Blocks corresponding to Kac, because they're not included in the global conformal blocks themselves. But they show up in the gluon OPE.
I'm sorry, whom is the question?
To Thomas.
To Thomas.
Oh,
just a continuation, yeah.
Oh yeah, you will have yes, you have an OP of let's say 2 gluons. Yes, you will have everything. You will have states exactly with dimensions which are integers plus I lambdas. So we have it's exactly what he was showing.
Right.
So the blocks, but then of course how it's related to. You're asking maybe question how it's whether that can be unified by Virasoro, yes, when you go to beyond the globe.
Yeah, Kac-Moody.
It's very, if I understand, that maybe somebody that would be very interesting if somebody could tell me if there is like there are techniques which exactly address this question: how from global conformal construct Virasoro blocks. Are you aware, Shuheng, are you aware of that? How this is done?
That's a good question. I don't know. Well, let me think. For the Kac-Moody, I certainly don't know the answer. Namely, if you take a generalized free vector and you compute its correlation function, it's labeled by some deltas. Mm-hmm. And you can ask whether that can be decomposed into some Kac-Moody block. But of course, you also have to say which level that Kac-Moody algebra is. I don't know whether this can always be done. I never thought about it. But that seems to be relevant.
I've seen U1 Kac-Moody blocks in something called warped CFT or some warped ADS CFT duality. They deal with something called U1 Kac-Moody blocks. But I don't think they have something for SUN or something. But even in the gravity case, how do we go from global to Virasoro here? That's probably an easier question anyway.
But do we expect for the gravity case? Well, I mean, let me see. Also, so you say if you scatter gravitons, I see. I don't know. I need to recall if you take a generalized free scalar and the correlation function that I just showed, and you restrict it to 2D. I don't remember whether that can be decomposed onto Virasoro blocks. I think I might have worked it out at some point, but I don't remember the answer.
Yeah, that's the simplest version of this question. Right, that's the simplest version. Do it for a free, for that type.
But in that case, we don't expect it to work, right? Because if you just have a free scalar in Minkowski space, if we don't have graviton in Minkowski space, maybe we don't expect Virasoro on the boundary.
Right. It would be really surprising. I can't see it.
Yeah.
Because we know how we get it.
Yeah. So one really needs to do this.
Yeah.
Monica has a question, I think. Yeah.
I had a comment on this. I think that there are at least formal expressions for how you sort of like the generalization of these OPE blocks to be Virasoro or like current algebra blocks. And the idea is that basically there's an analog of that kernel, but it involves addressing of either the current or like a sort of Wilson line of the current or either the stress tensor. So that as you expand it out order and order, it adds in like more factors of the current. So like Monica Goica has a paper in which she has some of these expressions and some other people do too. But they're at least like formal objects you can work with that include in principle all the Virasoro or current algebra descendants.
But that actually sounds surprising, right? Because wouldn't the expansion or the answer depend sensitively on the central charge and the scaling dimension? Because there will be sporadic null states as you vary C and delta.
Yeah, so that's a good question. I would agree.
I can imagine maybe in some large C or some heavy operator limits, this can be done, but
yeah,
it's probably not a completely general expression.
That's correct. So if it is, sorry, go on. Yeah.
But still just to check, even without constructing Kac-Moody blocks or anything, we could still check whether the OPE coefficient that sits in front of the conformal block associated to some of your bi-adjoint or higher adjoint states is the same OPE coefficient that we get in the Kac-Moody, the same OPE coefficient that it sits in front of the first Kac-Moody descendant that is there in, for example, my paper and Shamik's paper as well. So there's some, okay, maybe I should just go and check it, but yeah, if it works, then maybe everything will fit together.
I think the double trace piece doesn't actually factor, at least in generalized free field theory. Like the OPE coefficient. Maybe Shuhen can confirm.
Sorry, can you say again? I didn't quite follow.
The double trace OPE coefficient. Does it factor as 3 point square, or is it small? Is it
the OPE coefficient is the square? The coefficient in the conformal block decomposition is the square of the OPE coefficient. Is that what you were asking?
Yeah. You showed us the double trace coefficient, right?
Yeah, let me just show that again. Yeah, this coefficient here is supposed to be, is the square of the OPE coefficient.
So if it is really a free field, not a generalized one, you would have only the unit operator in 1.3. Is that correct?
No, you also have the all these operators.
Even for completely free, not generalized free field.
Yeah, you can set delta phi to be d-2/2. Well, you know, in 2D it's a little bit subtle, precisely because of the discussion we had yesterday. In 2D, phi is not really a good operator, and one has to go to the logarithmic branch. But once you are in 3D or higher, yeah, you can safely insert delta phi to be d-2/2. Here, d is the dimension of the generalized free field.
So what changes when you go to, because you mentioned something, but maybe I missed it. What changes when you go to actual free fields?
The only thing that changes is that one of this double trace operator is the stress tensor.
Okay, yeah. Yeah, so you have an energy momentum tensor then. Okay. Yeah. That's right, yes. It's going to be the one with the double derivative, yeah.
That's right.
Well,
and of course, alternatively, this function can be expanded on the principal series onto the conformal partial waves.
Yeah.
But perhaps it's the conformal block decomposition that's more physical in some sense. I'm not exactly sure.
Well, you can, I mean, you read exactly the squares of the structure constants. In that sense, yeah, and you read the spectrum. I mean, that's the one you should be looking at, I think.
For ordinary CFT, yes. Here, I'm a little bit less confident, but probably you are right.
Okay. And you mentioned something about probably a connection with Liouville theory. Maybe I missed that point.
It's a very superficial comment. I'm just saying that in Liouville, we also have a continuum of primary operators. And here it also seems to be the case, but it's a very superficial comment. I don't have anything deeper to say.
Well, mentioned yesterday that in our work, it looks like, well, at least in the shadow basis, the amplitudes, they look like they come from some kind of minimal models. And at one point, we're considering whether they have some connection with Liouville theory, because the dimensions exactly are continuous and they're not the ones of the minimal models that are discrete. So that's why I asked you, because it seems that we kind of got something like that, but we could not make it very solid because, okay, again, we kind of made a similar comment in our paper, but for minimal models. But again, dimensions are continuous, so that's interesting.
I'm also not sure if this interpretation in terms of generalized free field is correct for the most general choice of the conformal dimension. Because
Right.
if you choose general new i's, first of all, there will be contact terms. And I have to think a little bit more about what they mean for the boundary dual. And also the coefficients between the two terms will be different. So we have two terms coming from, you know, 1 goes to 3, 2 goes to 4, and 1 goes to 4, 2 goes to 3. But for general new i's, the coefficient will be different, and there will be some delta function of the new i's. Yeah, so I'm not exactly sure the general story. So I feel like I'm even having difficulty understanding the celestial dual for free field theory.
I see. Yeah. This,
But the celestial dual for free field theory might be sort of complicated. I mean, we wouldn't have, it would have, if we studied free fields in ADS and tried to relate that to ADS CFT holography.
But we know in ADS, we can take large N, and then there's a precise answer. In the large N limits.
yeah.
Wait, what N are you taking? Of Yang-Mills, you mean?
For example, we can take 4dn equals to 4 SUN and take large N and consider some scalar operator in 4dn equals to 4, perhaps in the 20-dimensional representation. And its correlation function in the large N limit is only contains the disconnected piece. Right? That's the usual large N spectral.
Why is that the analog of what you're doing? Because what you're doing, it seems like a very precise analog of just solving scalar wave equations in ADS, characterizing them in terms of representations of the boundary conformal group, and then free scalars, and then looking at boundary correlators.
I think it's related because we expect in large N CFT, all correlation functions factorize.
Mm-hmm.
And therefore they are just given by disconnected Witten diagrams. And once we arrive at those disconnected amplitudes, everything else just follows.
Well, maybe we should be looking for a large N example like that.
Sure, that would be much, yeah, indeed, that would be more satisfying indeed. But I would imagine if everything goes similar to ADS CFT, such a large N model in the large N limit will be effectively described by a free field.
Well, some things are going to go like ADS CFT and others won't. We don't know.
Yeah, we don't know. Yeah. Yeah.
Usually, free theory in ADS CFT is described by higher spin theory in the bulk, or you're referring also in taking large and limit in such a way as to decouple completely and becomes free. You know what? I thought you were getting higher spin theory in the bulk. Is that correct?
You have in mind free fields on the boundary corresponds to higher spins in the bulk?
Yeah.
Like in the OM model?
Yeah.
Yeah, but here I think it's slightly different. I mean, kinematically, if we don't talk about full-fledged ADS CFT, kinematically, people do talk about putting just a free massive scalar field in ADS. It's not gravity, just a free field. And
but we don't learn too much about holography by.
Well, I think we do. Well, to leading order we don't. But then we can do 1/n, and you can try to see what kind of consistent solutions to the bootstrap equation corresponds to consistent local interaction in ADS.
Yeah.
So yeah, here I only spelled out the leading order correspondence, and it would be interesting to add interactions. I didn't do that.
Do you have the same, let's see, so in my work with Alex and Anna and Walker, we had this funny factor of 1 over sine pi beta, which we never understood. Do you have exactly that same factor?
Sorry, what is beta again?
The sum of the sum of the I times the sum. Well, it's the sum of the conformal fact. Wait, is it
I don't think I don't think I do, right? Because here the beta dependence or the new I dependence is different from the connected piece. So here the new I dependence is just a delta function of the difference between the news or lambdas.
Okay.
Yeah.
So could you completely interpret this as, you know, a conformal block expansion with the square of OPEs and no funny factors? That hasn't happened in any other of the four. There's always something funny, right?
Right. But I think here because everything just works, all the formulas are just the same as the ordinary complex generalized free field. So the conformal block decomposition is almost standard, except up to that prefactor that I mentioned.
What was the prefactor? This sine pi beta was a prefactor that was.
That's true, but here is a different prefactor. So what's the prefactor? Blah blah blah. I think everything will work exactly in the same way, except for this. I think this is the analog of your sine 1 over sine.
That is the analog.
Right, right.
That is exactly the analog. It becomes a delta function when you you do something. You go to some limit.
Right.
When you
right.
go. Yeah.
So yeah, so this factor is still there. I don't have a good interpretation.
That's probably going to become 1 over sine pi. Yeah. You could probably derive this by some limiting procedure. Yeah.
Mm-hmm.
Okay, Alok, please go on.
Yeah, so I had a question for Shuheng. So Shuheng, have you looked at the kind of analog of the HKLL reconstruction in the sense of taking a bulk, just scalar field in flat space-time and seeing if one can do some kind of a, like a bulk to boundary Green's function analysis and recover a celestial generalized free field? I mean, reconstructing a bulk field in terms of the generalized free field like HKLL, even in the free field.
Oh.
Because I mean, it is important that we have a 3D boundary in the ADS case, right? So that we have this Green's function, bulk to boundary Green's function, and we can recover a bulk field in terms of, a smeared CFT field on the boundary.
Oh, I see what you mean.
Yeah.
No, I didn't do that. That's an interesting question. No, I didn't do that. Yeah.
I mean, if you didn't know ADS CFT, that would be a direct check, right, of the correspondence between generalized free field and then like a free field in ADS.
Yes, yes. Yeah, I very much hope that a similar story like what Puchinsky, Sully, and others did can be repeated here. Yeah.
Yeah. I mean, I think Marolf tried something like this in 2006, but he blew up spatial infinity. So you have like a hyperboloid. You basically have a boundary like for ADS. So it's like a 3-dimensional time-like boundary. And then, you can try to do this kind of analysis, but it's not a 4D, 2D reconstruction. It's a 4D, 3D reconstruction. So it's not clear how it would relate to the celestial free field, generalized. Yeah.
Yeah, I haven't thought about that. I think that's quite interesting. Yeah.
But now.
I also wondered the other thing, that in ordinary ADS-CFT, if you take a 4-point scalar function, a scalar 4-point function, generally it's not free, so it doesn't have this conformal block decomposition. But you can take the Lycon limit. Right? You can go to Lorentzian signature and go into the Lycon limit. And in the Lycon limit, it was known that the correlation function will behave very similar to a free field. And in particular, the large spin sector of the OP in the OPE will be very close to the generalized free field double trace operator. I wonder if there's a similar Lycon limit that can be set universally to all the celestial amplitudes. And maybe in that limit, all the celestial amplitudes look like a free field. That's actually very similar to Alok's comment. There should be something universal, one can say.
Andy, yeah, go on. You have a question?
Yeah, I have a question for Atal. Did the connection with, I'm wrestling with this business of which side you do the light ray transform on. Does the connection with twister theory, with the ambitwister, ambidextrous transform, does that specify a side?
No, I have been confused with the same thing. That it seems that if you want to make everything non-distributional, then there's one way to do it. If you do the
either way would make the 4-point function non-distributional.
That is true.
And the 2-point function.
Yeah.
It's only the 3-point function, and maybe it's only the 3-point function of massless particles. And
that requires this.
That's not such a weird formula, really. It's saying that only one chirality matters. But
no, it's actually much more natural to take positive helicity particles to twistor space, because then they're represented by wave functions of. Okay, it's actually historically much more natural. But at the level of these linearized gluons and gravitons, maybe you're right. It doesn't really matter beyond just the 3-point functions.
Wait, but which is more natural, the way you did it or the way I did it?
The thing I did was historically the thing that people do. They take positive helicity particles to twistor space by Fourier transforming lambda bar. Actually, what did I do? Yeah. So they take positive helicity particles to twistor space and negative helicity particles to dual twistor space. And thus, yeah, but am I saying this wrong, Lionel?
Well, I mean, we had this kind of 4D ambitwister string, which was really working. For n equals 4 CPI mills, we were using an n equals 3 version. But I mean, you were saying it the right way around in the sense that you wanted to do the, although I always get my conventions muddled, positive space and negative fidelity on dual twistor space. So if you want to do n equals 8 supergravity, you divide it up into 2 n equals 7 multiplets, or similarly for n equals 4, you divide it up into 2 n equals 3. But it wasn't clear how much you needed to do that. I mean, in the sense you got correct formally, I think, actually I'm not completely convinced of this, but I think you got correct formally whatever you did. So, and certainly going back to the 2009 papers when we were working in parallel with Freddie and Nemo, they were going absolutely ambidextrous with the positive helicity on twistor space and negative helicity on dual twistor space. But you could have done it the wrong way around. You could have done the negative helicity onto twistor space and the positive helicity onto dual twistor space. And we were just trying to be sort of almost Penrosian purists, saying we want to do everything onto twistor spaces. That was the coherent case. But I don't know if there's a correct answer here.
Yeah, but in any case,
the positive homogeneity seems correct for the, and so I think what you're doing seems to be the natural thing.
I basically copied the 2009 approach. Yeah, sorry.
What's puzzling is I don't see how the W symmetry would be kind of messed up. I don't see how to get the W symmetry doing it the other way around. But you guys had symmetry a half a century ago. So I don't see how I landed on the W symmetry doing the opposite thing as you.
So the W symmetry requires a positive homogeneity, positive helicity, positive homogeneity transform. Sorry, I haven't checked that the way you round. No, it must be the way you did it must be correct for that. Sorry,
it doesn't seem. You're saying that if you were to do it the other way, that I mean, the W symmetry would still be there, but it would become obscure somehow.
Yeah, be Fourier transformed in some sense.
Okay, well, if we're both doing the things that we think makes the W symmetry simple, act simply, how can we possibly be doing the opposite thing?
Yeah, sorry, yes, I haven't kept track of the signs, so I can't say for certain, but we land on your commutation relations.
Well,
tomorrow Lionel will explain to you.
Atul said for certain that we weren't, and I know that Monica.
But it's very easy to get muddled over.
Yeah,
I mean, it's very easy to get muddled over conventions as to which way round is which.
But Lionel, are you talking about helicity or the spinors, or lambda and lambda bar, or are you talking really physical helicity? Because I'm asking that because you can do anti-MHV, you can do anti-MHV representation, and then you seem to be doing, so is it the same thing if you write MHV as anti-MHV?
To make matters worse, when you do a shadow transform, you flip H minus H bar. So you might call that flipping the helicity, but you don't change the duality. So now I'm not sure, we haven't checked whether the light transform, what happened. So, right, so the shadow transform maps a self-dual graviton to a self-dual graviton, but flips its helicity.
But helicity also knows about frequency.
What?
Doesn't helicity also know about frequency? So if you talk about self-duality, then that doesn't factor in whether it's positive or negative frequency. Whereas helicity does factor in whether it's positive or negative frequency. Isn't that correct?
The shadow transform doesn't change positive or negative frequency.
Ah, okay.
We're in 2-2. So everything's real. It's too confusing to me to talk about self,
I mean, Z2 is the most complicated group to get right. It's just
So I secretly think that there is some subtlety here happening in 2-2 signature about the difference between wave function and a basis of wave functionals. So when you twistor transform the wave function, you actually dual twistor transform the wave functional basis. And I think the operator is somehow corresponding to the basis wave functional, and the twistor representative is the actual waveform. So all I have to do is sit down and carefully keep track of which thing is transforming to which side. And then, so I was thinking about this today. One good way to sort of answer Andy's question would be to take everything in a light transform basis and then convert the soft modes also into a light transform basis. Now, in the light transform basis, if my hope is correct, then Z bar is literally just this coordinate mu alpha dot. So in the light transform basis, the soft current should act as literally just two-dimensional diffeomorphisms associated to this z bar coordinate. So presumably we'll just see that in the soft theorem in the light transform basis. We just have to light transform the whole soft theorems along with the hard operators as well. We should be able to see some kind of symplectic diffeomorphism, the generators, like some derivatives acting on in the soft factors. And that should, yeah.
Well, we have all kinds of different conventions before we get to the actual amplitudes. But when we get to the amplitudes, it seems like we're talking about the same. There's no room for, and I think I wanted to transform the amplitudes in a way that leaves the singular. I thought that the W symmetry becomes manifest in when you light transform on the side that preserves the singularity in the 3-point function. And you're light transforming on the other side, and you have some other way of understanding the W infinity. Not in terms of operators in the theory, I guess.
Right. Yeah, no, we don't. So I don't have a way of understanding W infinity just yet in 2-2 signature, but we have an auxiliary sort of twistor model, twistor sigma model way of understanding W infinity, which sort of identifies the MHV amplitude with the Kähler scalar, which Lionel will talk about tomorrow.
But I'm sure we must be both working the same way around. I find it difficult to believe otherwise. But I can't commit myself to that without.
I just need to sit down and do this.
So with the 3-point
I
function,
did sit down, I couldn't figure it out.
Yeah.
I think the 3-point function has to be singular, doesn't it? Because it's local on twisted.
Yeah, but you can go either way. With 3-point function, you can go either way. You can say all z bars equal or z equal. So then you have a MHV and anti-MHV, yes? So
yes.
What's the rule here? Yes?
So if you light transform the positive velocity ones in Z and the negative velocity ones in Z bar, then you use up the momentum conserving delta functions in both MHV and anti-MHV symmetrically. But if you do the other way around, then you don't use up anything. And so, yeah.
Well, you use up one thing, right?
Yeah, you
use up one of the momentum conserving delta function.
Yeah, if you light transform the opposite way, use up only one of the delta functions, and then the other one is still there.
Yeah, you do use one of them.
I have a question for Hernan. You had this formula for this factorization formula in non-abelian gauge theory.
Yes.
In which you pulled out some soft piece that looked like some sort of Kac-Moody correlator, right?
Yes, yes. Mm-hmm.
How far are you? So I think, well, actually, I've been perennially confused about this, to what extent there are infrared finite amplitudes in non-abelian gauge theory. But you're perilously close. So we had formulas like that in gravity and abelian gauge theory, as you know, and we understood the dressing, the Fedyaev-Coolidge, or the clouds of soft photons, is sort of a generalization of Fedyaev-Coolidge, where you allow them to be incoming or outgoing, in terms of just peeling off. In other words, the dressed amplitudes are equal to the hard part of the amplitude. And that shows that there's no problem with infrared divergences in QED or gravity. How close are you to being able to, you didn't mention that, how close are you being able to do that in the non-abelian?
Okay, I'm not sure if there exists like a similar Fedyaev-Coolidge dressing in QCD, or I don't know if it is as successful as in QED. For the moment, we have been trying to understand these correlators.
I think there isn't such a thing, but your formula might suggest what it should be. Well, people like Lorenzo Magni and other people, there's something. I'm confused about what the status of it is. Yeah.
From our analysis, we didn't like consider this Fedyaev-Coolidge dressing yet, because we were more focused on understanding this set factor as a correlator. But of course, then you should try to answer this question of whether you can write the whole amplitude as some correlation function of dressed operators. But yeah, for the time being, I don't know how to answer your question. Maybe Lorenzo knows more. Yeah, perfect.
Yeah. Can you hear me?
Oh yeah.
Yeah.
Oh,
hi.
I didn't.
I unfortunately I had to miss some stuff this afternoon because I had other things. But so there is quite a bit of history on the non-abelian version of Fedyaev-Coolidge. However, sort of most of the things that have been done in the past 20 years or so didn't really use that language. So I would say there are two problems. One is just the fact that one would have to sort of translate back. There are a lot of formal expressions for the coherent states in the non-abelian case. But what people are normally using now is basically not that formulation. And then the other thing is, of course, that in the non-abelian case, you simply have to in the non-abelian case, you simply have to deal with the collinear divergences, and which sort of in the QED case, you can just let the electron be massive and you forget all about that. That makes quite a bit of a difference because the collinear divergences don't have a simple structure, allow me in some sense, as the soft divergences, you get an infinite series of BCH type commutators. So there are a couple of problems in sort of mapping these things to the coherent state approach, to the Fedyaev-Coolidge type of approach. And I think both what Hernan and Francisco have done and what I have done, we really use a rather different kind of language. So mapping back would require some work.
Could those collinear divergences be related to this business of there might be a biadjoint in the OPE of?
I certainly don't know, but what I do think, and from I understand these things only to a limited extent, but what I would certainly say is that the collinear stuff will begin to emerge inside some OPE. So what you get is the two. You take two particles, you take them close, the Z's become, they tend to the same Z on the sphere. And certainly what you get out of that is at least a piece of the collinear stuff. That's
Lorenzo, actually, I don't know if you are aware that part of subleading divergences, I would say 1/2, can be represented by graviton amplitudes. So that's something. So in other words, when you have a leading, of course, you have a leading collinear limit, and then you have a subleading, even at the tree level, the subleading collinear, they can be related to the amplitudes which involve insertion of graviton. So that's maybe that may be related actually to Andy's point.
Yeah, that would be quite interesting and also somehow counterintuitive. But I should also qualify what I said. That all that I've been saying is leading power in the either soft or collinear limit. So what you normally discuss is sort of next to soft theorems. Those are next to soft in the sense that they are 1 power down in the energy. And I'm not sure whether you are playing the same game with collinear now. So can one make any statement?
When I talk subleading collinear, which means subleading in the whatever, it's subleading in
KT. So
no, subleading in a sense that usually in our language in celestial when the z's goes coincide, yes, which means then lambda 1 goes to lambda 2, the spinners.
Okay. I mean, it's interesting because in some sense, people never look at the collinear stuff for gravity because there is this law which is correct that it cancels by momentum conservation. So if there is some message from collinear gravity to be brought back to gauge theories, it's certainly very interesting. And I was not aware.
No, actually, it's collinear of Young-Mills, which is.
Well,
yes. No, actually, you can go also either way. And we can invert those relations. Yes.
Okay. Well, I think thanks.
You're saying, Tom, that if you add a graviton, that gives an amplitude which is equal to the collinear limit of the. But surely his question has an answer in a theory with no gravitons, right?
Yeah, so it's formally, yeah. So yes, that's true. So you have a Young-Mills. That's the old work with which we did with Stefan some long ago. Okay, so you have 2 gluons, which become collinear, and you have n plus 2 gluons. You start with. You make 2 collinear. And this amplitude will be you know what is the leading collinear divergence, but subleading collinear divergence will be related to the amplitude in which have n gluons and the graviton. So subleading term, and you will call it subleading OP term in a celestial language, yes, because it's of order. It doesn't go like 1 over ZIJ, but it goes like, I think it goes like Z divided by Z bar or something like that.
Yeah, okay, that's very interesting.
But this is in 3 level, right, Tom? Or... That's
3 level, yeah. That is the base of this, that what we are doing later when essentially representing gravitons, you can go invert this relation, and that what you can Einstein-Young-Mills amplitudes can be expressed as Young-Mills amplitude, but not as a double copy. These are linear equations, linear relations in which amplitude with 1 graviton is related to the amplitude with 2 gluons replacing the graviton.
So does that mean, do you want to describe this, Tom, as saying that if we look at the singlet term in the OPE of 2 gluons, that we have a term which is just, in the OPE, we have a term which is 2 normal ordered gluons plus a graviton, or do you want to identify the 2 normal ordered gluons as the same operator as the graviton?
I would say that would identify the graviton, but I'm not completely sure about it. I didn't think about it in those terms.
But what
do you do with saying that there's a null state, which is somehow a graviton minus 2?
Yes, so now the graviton gets replaced, graviton replaced by 2 gluons. Yes, so that was the, okay, if you push it far, okay, then that is the always thing okay, so that gravitons from that point of view looks like 2 gluons, okay?
But what do you do with the colors? What do you do with the colors of the gluons?
Oh, it's one, oh yeah, that's again tricky because you like to partial amplitudes, which you strip from colors.
Okay, very good, thanks. That's
So it's like some combination of partials. So it's not a very direct relation. That's something which is really, it's very mysterious relation. Okay, in other words, you have to, of course, you are right. You have to remove the color. Okay, but you do it by mixing various partial amplitudes by stripping color.
Yes. So you do use the trace basis?
Yeah, you can use trace base for partials, yes, of course, yeah. So, yeah. So from that point of view, and coming back to your question, that actually is that's why this relation which you would like to have, that you have you can see somehow subleading OP as a graviton, that is not so straightforward because there's this relation somehow, in these relations, it's not clear what's happening with color indices, with the group indices. Yes, it's not delta AB. It's not simply that as simple as that two. You have an OP. You have just singlet, which appears, which turns out to be graviton.
Yeah. Was there a question, I think, from Francisco or Atul? Francisco, I think you had raised your hand.
No, thanks, Thomas. No, Thomas, I think answered my question already. Thank you.
Atul had a question, I think. Yeah, correct.
I had a question for Alfredo, actually.
Mm-hmm.
So, he's still here.
Yeah.
When reading Kravchuk and Simmons-Duffin, there is a statement in that paper that at least in a standard-ish CFT which is unitary, and or not even unitary, a CFT which just has the lowest energy vacuum, the light transform of a local operator always has to annihilate the vacuum.
Right.
And so the issue is that if you take a time-ordered correlation function of just light transforms of local operators, this is something I didn't manage to mention at the end of my talk. I just remembered I should have. This is the scary bit. A time-ordered correlation function of just light transformed local operators necessarily has to vanish, because in a Lorentzian CFTs where you have some time ordering, because the light transform for local operator always annihilates the vacuum. Now, are we getting around, but in CCFT, as I showed, and as you also calculated, I think for 2-point functions of 2 light transformed operators, the answers are non-zero because there's not much of a so in a usual CFT, you can do some contour integral and you can show that a 3-point function vanishes with appropriate I epsilon prescriptions. But here, there's no such I epsilon prescription needed because everything localized on the delta function. So how do you think we are getting around this fact that the light transform of a local operator has to annihilate the vacuum? Is there no vacuum in a celestial CFT, or is there no time ordering, or are the operators that we are light transforming not really local secretly? Or
so
anyone else? Yeah, no, I just wanted to put this.
That's probably explained in the paper as well. The point is that the 3-point functions vanish, so you can compute, let's say, 3-point function of a light ray operator with 2 scalar operators. That 3-point function vanishes unless you are in a particular setup. And let me see how this goes.
You mean a particular order?
Yeah, a particular order. So
yeah. So
that was exactly my question. Yeah, I think so.
Yeah, so you have to be in a setup where two operators are space-like separated, and then you integrate your lighter operator between those two. So that doesn't the time order correlation function doesn't vanish in that setup. So it's only non-trivial in that setup, because basically the lighter operator is between the two scalar ones, so it's not hitting the vacuum. If it hits the vacuum, it vanishes.
But this is probably my question. I think I could probably ask that. Presumably, operators, it's non-local operators and light rays, they annihilate the vacuum under a theorem by Mach, which assumes positive energy and says continuous spin operators must annihilate the vacuum, which doesn't seem to be the case here. That was my question I had. How, I haven't seen the proof of the theorem, so I don't know if it makes any difference or not, but how does it go here? Because you used it in the paper, I know, because I read yesterday. How can we, do we still assume that the light ray operators annihilate the vacuum, and why is that?
Yeah, they do. The actual 3-point functions where the light ray operator hits the vacuum are 0. It's just that the time order 3-point function is defined piecewise, and it happens not to vanish. So it coincides with the standard 3-point function only in this setup where the light ray operator happens to be in between the two scalar ones. So that's the only non-trivial case. Because, well, in the way I computed, of course, in one case you can deform the counter upwards, on the other case you can deform it downwards, and it's 0. The only case where you don't get a 0 contribution is where the counter hacks one of the branches. And that happens because the light ray operator is precisely in between the two scalar ones. And there is no contradiction there, I think.
I see. So in your case, it doesn't vanish. It does vanish, because I was worried, because in my case, it doesn't vanish because I'm taking a 3-point amplitude and I'm light transforming all 3 gluons.
But we're taking time order correlation. So the time order correlation function doesn't vanish, because in that case, the light ray operator doesn't hit the vacuum if you are in the right setup, of course.
No, also, if I remember from what those guys did, the locations of the other 2 operators is considered taken to be generic, which you can do in a CFT, in a normal type of CFT. Basically, if all of this non-vanishing comes from the I epsilon prescription, and you have to do some contour deformation. And the I epsilon prescription gives us a vanishing result if the location of the other operators can be chosen generically. But in a celestial CFT, precisely because of momentum conserving that delta function, you don't really have the freedom of moving around the locations of the other operators. So I don't think in a celestial CFT that it immediately follows that light ray operator should annihilate the vacuum.
Conclusion there might rather be that celestial CFT is not a CFT rather than the light ray, because a CFT might never be able to generate a momentum conserving delta function if it's a correlative. Well, what I concluded was that the operators dual to boost eigenstates may secretly not be local operators after all. And these that's why their light transformed correlation functions are secretly not vanishing. Because that's what I want to conclude.
Wait a second.
I think that's also true.
Yeah, when I say time order correlation function, I don't mean that the light ray operator is time order. I mean the light ray transform of a correlation function.
Right.
Suhin, you want to say something?
Sorry, I'm just confused. So what's the verdict? Does the light ray operator annihilate the vacuum or not?
Is there a vacuum in celestial CFT of lowest energy? I mean,
well, the 3-point function vanishes, at least for the scalar case.
But why? what's the underlying physics reason for that? Or are you saying that it
because
just
otherwise a light transform acting on the vacuum would generate a negative energy state?
But why do we care in celestial sphere? Is that the right norm to use? I mean, ordinary CFT, I understand that's the reason, but I'm asking what about in celestial CFT?
No, I don't know. And I would hope that there's some issues that it's not the right thing to use, and that's why there is a non-vanishing answer. I would like that to be the case. But I wanted to ask in case. Yeah.
I think that, there's a little bit of history here. The first ones that were, well, if you just solve the wave equations, so in our first paper on this, Shuhong and I and Sabrina were just like solving the wave equations, and there's no difference between what we're calling the conformal primaries and the shadow conformal, but you could have called either one the good one. And that speaks to very much to what you're saying, Atul. The conformal, let me call them melon primaries because they're related, and that only makes sense for the massless fields. The melon primaries are related by a simple formula to momentum plane waves, which the whole subject could have proceeded without ever discussing momentum, momentum eigenstates. And those, the melon primaries, at infinity, their Klein-Gordon current pierces the celestial sphere at a point. And I think that's also true for the shadow. Is that, you're nodding, Shuhong? It's also true for the shadows, right?
Yeah, I think so, yeah. I mean, on the celestial sphere.
It's true for the light transform ones, probably. So it's not clear which one, it's clear that they're not, we can't call all of them a complete set of local operators, but I think it's totally plausible that, that the true set of local operators are the ones where everything is good, could be the light transform operators or something else. So that, yeah.
I mean, definitely the conformal primary operators with for generic dimension, they can't be local because don't we have this property that the shadow transform of a conformal primary with weight delta is the conformal primary with weight d minus delta? So this means that so basically, if I vary over deltas, you have a relationship between the operators with dimension delta and d minus delta as the shadow transform, which is a non-local transformation. So how can an operator with dimension delta for generic values of delta be local? Does that make sense?
Yeah, but maybe some set of them, there's a basis of
set of them are mutually local.
Yeah.
Set of them could be. I mean, that often happens in conformal field theory. You're handed a Lagrangian and you're some operators and you compute there, and then there's examples where you have Lagrangians and you take different subsets of the operators that you can construct that give you different conformal field theories, different extractions of the mutually local set of operators that are different extractions of the total set of operators whose OPEs are mutually local that define different conformal field theories. Yeah, so I think we don't know.
Well, while we are at it, usually in ordinary CFT, those different choices can be related by gauging, right? So I don't know if there's a similar story here, right? Like in Ising model, if you gauge the Z2, you throw away the order operator, but you bring in the disorder operator. And maybe there's something similar here. I don't have anything concrete to say, but maybe the choices of what one might call the local operator on the celestial sphere, there might be some discrete choices related by some governed by some symmetry principle. I don't know.
what would be really nice, I mean, it's really kind of interesting, you know, I'm beginning to appreciate how good we had it in ordinary conformal field theory, because in ordinary conformal field theory, there's almost never any discussion of what happens when operators are coincident. And, but in fact, in various contexts, it's known that you, for various consistency constraints and so on, that you have to have contact terms. But for some reason, this hardly ever gets discussed. And here we have to keep track of those contact terms, and they're a pain. And that was what all this discussion was yesterday about the celestial diamond. There was contact terms in there, and you know, and here we have to keep track of all the contact terms, which it's not inconsistent, but it's messy. And it would be really nice if there was some basis in which it's like the conformal field theories that we're used to, where all the information is encoded in correlation functions at distinct points.
Well, but in ordinary quantum field theory, it's precisely the anomalies that are captured by those contact terms. Right? So I would say they are also important and discussed in the literature.
I think for generic OPEs, you don't need to consider it, because you'll only possibly get the contact terms if the delta 1 plus delta 2 is equal to the dimension of space-time, or plus an integer, something like that. So only if you have some special values of these deltas, which are precisely the ones that show up in celestial CFTs, would you even have to worry about.
Well, but that's also the case for ordinary global symmetry in ordinary quantum field theory, right?
That's what I'm saying.
Right, yeah.
I think in ordinary CFT, it is discussed. It's just in most CFTs, you don't have these very special choices of deltas. You know, they take some random irrational values. Anyways.
Right, but whenever you have a global symmetry, then you have a Noether curve with that specific scaling dimension. And then they are interested in contact terms encoding the anomaly of those global symmetries.
But I'm confused. What the contact terms we have here is they are on the worldsheet or actually on the celestial sphere. Were you referring to the dimension? I thought, well, I mean, we get delta functions, right? Of course, it's dependent on the dimensions of the operators, but so is that what you're saying, that basically the delta functions are the result of specific dimensions, and because of the
yeah, delta function has specific scaling dimensions, so you will only appear in OPE between operators with some very specific scaling dimensions.
And these scaling dimensions, they come from momentum conservation in our case at the end of the day. They relate to lambdas, or not momentum conservation, I'm sorry, by scaling bias, if I remember, in Gates theory, right? Yeah. It's bizarre. But actually the shadow transform, that's what it does. It kind of like takes this, that's what Andy said, takes these delta functions and makes them basically terms that we like. Normally in CFT, we would throw them away, right?
Yes, but sometimes it has the irritating feature of it takes the delta functions that that we like and turns them into nice smooth things, and at the same time taking nice smooth things and collapsing them to delta functions.
Yeah, it's kind of a local place,
but that's one of the things I think interesting about what Eitel did. It seemed to be a consistent prescription that seems to eliminate all delta functions. Though it would be nice, as a question for Eitel, it would be nice to extend the prescription to everything, to scalars and.
Mm-hmm.
Yeah, that's also, so I only evaluated the 3-point functions in some particular incoming outgoing configurations. I still have to do the other cases. And of course, the momentum conserving delta functions will get absorbed. because they will just get absorbed. But the last few integrals need to be handled carefully with regards to what branch I pick and stuff like that.
Yeah.
Because, yeah.
Can these light transforms? Sorry, go on. Sorry.
No, I was just wondering, how would I do this for scalars actually? But if I just by hand.
You can just light transform, and then all the scalars have spin 1, which sounds kind of interesting.
Is it is there a 3-point massless scalar amplitude?
No,
what does it say? No, right? So there's no issue to solve there, I suppose. Is there?
No, that has to be computed.
Yeah, there's an issue. You know, suppose we want to compute the 4-point scalar.
All right.
And what do we do about massive stuff? I guess massive stuff is self-shadow. So does that mean we don't, we just leave it alone? Is that? What would the general proposal be for a general correlation function? So that it looks like everything is smooth and we never have to think about contact terms. Maybe it would be that you always shadow positive helicity, or whatever. You always you always light transform in the way that you suggest if there's a helicity. And then what do you do when you run into a scalar, a massless scalar? I guess that's the only case that you didn't address.
Yeah. Also, well, it's also an interesting question whether we should do anything to the massive scalar, or should we leave it alone? It's already good.
What could we do to it? It's, oh, wait, light transform, it's self-shadow, but what's its light? Oh, its light transform will be something different, right? Its light transform. Its light transform will be a spin 1 field. So there'll be 2 helicities. There'll be 2, you could have spin plus, isn't that right? Yeah.
Yeah, there are two light transforms, and they are related by Shao.
Right. So there's really only one.
Yeah.
Oh wait, no. There's a positive helicity and a negative helicity. That sounds kind of fun.
Oh, okay. You mean the light transform thing might have different helicities.
Yeah.
Can I ask how can this procedure be applied to the free massive scalar that we were discussing earlier? So there,
I mean,
when you go to the conformal basis, you also have the contact terms and the power law terms, and they kind of mixed together. Does your recipe apply?
In the massive scalar, you have contact terms. What was the contact term in the massive scalar case?
In the massive case, you know, when I go
you're talking about the massless case. Sorry.
I was thinking about a massive case. And there, in the conformal basis, the correlation function contain power law terms and contact terms. I was just wondering.
Contact terms in Z. I thought contact terms in delta.
Also in Z, right? The reason is simple. It's just because when you do this change of basis, you need to use the completeness relation of the bulk to boundary propagator in hyperbolic space. And the completeness relation involves the power law term and the contact term. Both of them appear. In my presentation, I chose some specific nu to ignore the contact terms, but for more general nu i's, there will be contact terms. So I was just wondering, since this is such a simple correlation function, is there some generalization of your recipe that can help us disentangle these two pieces?
Yeah, I wouldn't really know. The main reason being there is no generalization of the twistor construction to massive particles anyway.
Right.
So I wouldn't even be able to motivate it from that direction. But yeah, in all honesty, I haven't thought about massive cases.
Okay. The only thing I'll note about the massive case is that the only thing I'll note about Shuhang's questions, sorry, Andy, is that if you do a shadow transform on one of them, the power law term becomes the contact term and the contact term becomes the power law term. They actually exchange. Maybe some linear combination of the field and its shadow can cancel off the contact term.
Maybe.
Oh, that's why the light transform helps, because it's only half a shadow. So it's sort of...
But on the other hand, why do we hate the contact term that much? I mean, ordinary CFT, the contact terms tell us a lot about the anomalies, and some of the contact terms can be moved around by adding appropriate counter terms. But there are some combinations of them encoding important information of the CFT.
I don't think we hate the contact terms. We just want to be able to learn everything that we can. In ordinary CFT, you learn everything by looking at correlation functions at separated points. And you can even from those deduce what the contact terms must be.
That's true.
We'd like to be in that situation.
Okay. Okay, that's a fair question.
I mean, maybe it doesn't work that way, but it doesn't seem ruled out.
Is there a light transform in higher dimensions?
Yeah, light transform works in any Lorentzian CFT. It's just that it's not going to double to give a shadow transform, I think.
Okay.
Because light transform is only along an LGDC, while shadow is everything. Yeah. Yeah, my only reason for playing around with these light transforms and not wanting a contact term was because I want to, I would like to call an operator local if it gives the simplest form of a 3-point function. But that's only philosophical, of course. Also, the OPE coefficient, that beta function, was not manifest in the original 3-point celestial amplitude. If it's getting manifest in some sense here, then that's also better.
But it would be unavoidable because the dimensions are specifically d/2 plus I lambda. So, if I take delta 1 plus delta 2, that's an integer, which is equal to the dimension of space-time. So even in normal CFTs, when you have such type of operators whose dimensions add up to the dimension of the space, then you have contact terms. So it might actually be unavoidable and in fact be a feature of the fact that we're in principal series representation.
Yeah, it might happen that I might need to be even more careful with my light transform calculation. Maybe some secret additive contact term might get generated, which just like your shadow transform is generating an additive contact term. Maybe I just have to be more careful with my I epsilon prescriptions, and something will show up there as well. In any case, I need to sit down and compute the light transform OPEs and all that stuff to see whether all of this is useful in any sense.
But Alfredo seems to have computed most of them, haven't you?
So the light ray transforms can be extracted from these OPE blocks easily, but I didn't compute the left-hand side. I didn't light transform the left-hand side. So I guess what Atul was doing is to actually compute the OPE of two light ray operators going to a light ray operator.
Yeah, that.
Yeah. So I think that the block can be used, but you have to light transform the block itself. So that's
You've set it up.
Good idea. I'll do that. Yeah.
I have a question for Shuheng. Maybe it was answered. AC said I miss your. I'm sorry, I kind of miss your part of the discussion. But I'm still curious about this GFT. So you actually decompose your say your disconnected amplitude, right? You decompose that disconnected amplitude. You can write it into the GFT form and then partial wave expand it.
Yeah.
Right. And this partial wave expansion happens in 2 dimensions. So, right?
Yes. Well, I presented it in general dimensions, but yes.
But in 3D, say you only have one chirality, so it's not the same expansion, right?
No, there's a formula that
I mean 1D, not 3D, but you mean like what you did with Lam and Shao in your paper, you actually expanded.
So the general expansion looks like this. So it's a sum over spin and then a sum over an integer.
Yeah, but that if I wanted to write down the same expansion in 1 dimension, right?
Right.
I can't read it up from there because I have there you have conformal blocks for both chiralities.
Right. In 1 dimension, I think it can be continued from this formula. But if not, there's also a paper doing that very explicitly. I think Anna Maria cited that paper in her talk. Yes.
Yeah, the alpha space paper, yes.
Right. I think we even discussed that paper at some point. Yes, now I remember.
I remember. But okay, but in this 2-dimensional decomposition, so you seem to be finding a matching for the structure constants, right? So the coefficients, you say they actually square. If you, is that what you're saying? This one's square as 3 point.
This is a positive number, and it's the square of the OPE coefficient.
Of what OPE coefficient?
Between this is generalized free field between phi and the double trace operator.
And what do you make of the double trace operator in the scattering amplitude? So here you don't have, say, beta Soro descendants or Kathmudi descendants. So what are these double trace operators?
In the celestial story, I'm not sure. Here I'm just stating that we get the same function as a full point function, and that can be expanded onto blocks. I don't have a clear picture on what the celestial OPE will mean. Maybe you have a better idea.
If we were to write the optical theorem for at loop level, we will have multi-particle states.
Right.
I suspect that if you write it in terms of partial waves, that's probably the origin of these double trace operators. But I'm still puzzled that they are still there at 3-level scalar theory, which is really simple.
Yes. Yeah, I don't know how to interpret those double trace exchange from the celestial point of view. Maybe there are some n-particle states, but it's weird to say those words because it's really a free theory. There's no bound state whatsoever.
But in the bulk there are bound states, right?
The bulk is literally a free massive scalar field.
Oh, this one is a free. Yes, you are right. So this one is the what you call the disconnected part. Okay.
That's right. I'm only looking at the disconnected part. Yes. So there's no bound state whatsoever.
And so you were saying that this is dominant with respect to the connected part, or why would this be?
Yeah, in a weakly couple perturbation theory, and this will be the leading contribution.
But is there an operator product expansion?
That I'm not sure. I don't know.
Aren't you sort of, well, you wrote all operator product coefficients, or their squares.
Well, the only comment I was only saying that the 4-point function, the celestial amplitudes can be decomposed onto blocks, and there are coefficients there. Andy, are you asking this sentence or?
Yeah, are those OPE coefficients somehow?
Sorry. This part of the notes is reviewing generalized free fields in the context of ordinary ADS CFT. So this is the OPE for just the generalized free field. It's not an OPE in flat space. So yeah, you can ignore the sentence if you want. I don't have a picture for OPE here.
But isn't your analysis suggesting that there's some sense in which two free scalars have an OPE which produces that operator phi with a bunch of derivatives and another phi?
Yeah.
And what's wrong with that? Because there's a line between them.
Should I think about it as a two-particle state, maybe? But there's no bonding energy. There's no binding energy between them.
Well, we don't really want to talk about binding energy. We're not working in an energy basis at all, right?
Yeah.
So,
okay, that's true.
I'm sorry, I'm gonna stop the recording now because I feel we're
okay.
Time. Just to let you know that I'm stopping the recording. By all means,